Okay, folks. So in this video, I will explain about specific activity. And before that, let's recall the radioactivity or the activity, which was R equal to decay constant and the number of nuclei. Okay, this is the formulation for radioactivity. Okay. And specific activity is activity, the unit for activity if in SI unit is in becquerel. Okay. And for specific activity, okay, let's think about its definition. Okay, the definition is activity per unit mass. Okay. So the unit could become as a becquerel per kg if you want it in SI, or if your radioactive material is small, the mass is small, you can express is in becquerel per gram. Okay. And okay, let's say you have, this is your radioactive sample. Okay. It could be, it doesn't necessarily have to be solid. Okay, it could be liquid as well. Okay, so solid or liquid, and gas as well. If you can, if you know the mass of the gas, okay, you can express uh, the specificity of the gas, but uh, uh in practical, okay, in practice, we don't express the gas, radioactive gas, um, in specific activity. Okay, so usually applied for liquid and solid. Okay, so if this is your radioactive sample, okay, let's say it has 500 becquerel, okay, and mass is let's say 50 gram. Okay, so the specific activity is 500 becquerel over 50 gram. Okay, so it is 10 becquerel per gram. So the specific activity, so if you have 1 gram of this, if you possess 1 gram of the sample, then the activity of the sample is 10 BQ. Okay, meaning that the sample is decaying at the rate of 10 decay per second. Okay, so if let's say if you possess 2 gram, then the activity will be double, which is 20. So that's specific activity for sample. Okay, for sample, this for non pure sample. Okay, meaning that uh, there are radionuclides inside the sample, as well as other nuclear species, or as well as other nuclide. So so what so you know, you measure the activity of the sample as well as the mass, then you can determine the specific activity. But what if the sample, okay, the constituent of the sample is pure, okay, pure sample, meaning that only there's only one radionuclide. Okay? Only one nuclide species. There's only one type. Okay, one type of radionuclides. So let's say thorium. Okay, let's say you have thorium. Okay, the sample consists of 100% thorium. Okay, so if this is the situation, okay, then according to the definition of specific activity, which is mass, not mass, which is activity per mass. Okay, per mass. Okay, so if this is the case, okay, then you only need to know. Then you only need to know what is the decay constant of thorium, okay, and its molar mass. Okay, so how could this be simplified? Is because it is because okay, let's say okay, so in this case, all all nuclei are thorium. Okay, I just pick up thorium for the example. Okay, it could be other nuclide as well. Okay, so let's say thorium. Okay, so for mass, okay, as we know, okay, as we all know, mass is equal to uh, before mass. Okay, I think better we start with mole. Okay, so let's if you forget chemistry, please do some revision. Okay, so let's start with mole. Okay, so mole, as we all know, is the mass over uh, molecular weight. Okay, if your compound is in molecule, but in our case it's just the thorium. Okay, so it is more appropriate if we use atomic weight. Okay, so so this is equation 1. Okay, and then as we all know, okay, number of atom, okay, equal to mole multiply with the Avogadro constant. So this is, let's say this is equation number 2. So from mass, the denominator, okay, mass here, okay, is can be deduced from equation 1. Okay, and activity, okay, while the activity is decay constant, okay, multiply with the present number of nuclei, okay, like I said here, okay, this one, this formula. So what happened to the mass here? Okay, so from equation 1, okay, we can determine mass, which is equal to mole times the atomic weight. And from equation 2, okay, mole equal to the number of atom divided with Avogadro. Okay, so therefore, our formula for specific activity becomes lambda n over mass. Okay, mass here is mole time atomic weight. Okay. And so mass equal to mole multiply atomic weight. So mole, I'm going to use equation the relationship from equation number 2. Okay, so become number of atoms. Okay, over the Avogadro constant. So that is for the mole. Okay, times the atomic weight. Okay. So number of atom, the number of atom is actually is exactly the same as the number of nuclei n. Okay. So I can transform the equation that become number of atom equal to number of nuclei. Okay, so become n. So AV times the atomic weight. Okay, previously I introduced m. Okay, so at the end, you get lambda Avogadro number divided with the atomic weight. Okay, so this is when you have pure sample. Okay, for example, let's say tritium. So tritium. Okay, so if all nuclei in the sample are tritium, okay, so then the specific activity for this tritium sample is equal to lambda Avogadro constant over em, the atomic weight of the tritium. Okay. So okay, by the way, the half-life of tritium is 12.26 years. Okay. So since we want the final answer in becquerel per gram, okay, so you have to convert the times. Okay. So this is the half-life of the lithium. Okay, so you have to convert the time and anything that is in unit time into a second. Okay, so lambda is ln 2 over t half. Okay, multiply with AV, okay, over m. Okay, so ln 2 over, okay, so this one you must convert 12.26 years into second. Okay, so how many seconds is that? So it will be down here. Okay, multiply with the Avogadro constant, 6.02 10 to the minus 10 to the power of 23. Okay, no nuclei per mole. Okay, over the atomic weight. of the tritium, which is 3. Okay, 3 uh, 3 gram per mole. Okay, so why 3? Because tritium is actually the hydrogen 3. Okay, it is hydrogen with two neutron. Okay, that is tritium. So its atomic weight is 3. Okay, meaning that you for to 3 you need 3 gram. You need 3 gram of tritium, so that you have a mole of tritium. Okay, so that's is the meaning, and you calculate. Okay, if you perform the calculation, okay, the final answer will be in becquerel per gram. Okay, that's one example for specific activity of pure sample. Okay, so that's for the specific activity.